Well, hello everyone. I'm Ira Feldman. I'm the Executive Director of MEPTEC. I'd like to welcome you to today's Semiconductor Industry Speaker Series that we co-sponsor with IMAPS. So welcome. Good morning to you, good afternoon, good evening to you, depending upon where you are around the world. The great thing about virtualizing our speaker series is we can reach audiences far beyond Silicon Valley. So welcome to everybody who is on the line and watching, and also the people who are going to watch it later on our YouTube channel. So welcome. I hope you enjoyed today's presentation. Semiconductor Industry Speaker Series is at least monthly, but some months we now have 2 presentations due to the high level of interest. So our next presentation will be on July 1st. Stephen Rothrock from AT-Reg will talk about the US-China trade war and the tariff effects on the global OSAT market. And then followed by July 15th, Jan Vardaman from TechSearch International will give a global market update. These all start at 11:30 Pacific time on July 1st, July 15th. We'll have some announcements. Signups will be on the MEPTEC website, and then we will announce our presentations for August, certainly on August 12th, and we'll probably have at least one more in August. So please join us, and if you would like to speak at a future webinar or luncheons once they resume, please contact myself or Dave Town. So, MEPTEC has scheduled on Wednesday, September 16th, back at Semi headquarters, the Known Good Die workshop. Our keynote will be David Greenlaw. We have technical presentations from Cisco, Advantest, Synopsys, Mollmauer, FormFactor, and others. But with the current stay-at-home order, we've decided to add a panel discussion. We're going to, it's called Who Cares About Known Good Die? Heterogeneous integration is where the action is. So we're going to have a lively discussion on is known good die needed? What are the implications in today's world of heterogeneous integration? This will be on June 30th at 9:30 a.m. Pacific time. There are sign-up links on the MEPTEC website, so please join us for that on June 30th. So today's presentation is design of miniature multi-mode SiP modules with 2 integrated antennas by Chris Barratt from Insight SiP. Chris is the CTO and founder of Insight SiP. He is an engineering graduate from Cambridge and London universities in the UK with over 40 years of experience in RF and microwave design, especially in the area of active circuits and antennas. And he's been leading, doing RF SiP design since 2000. And prior to founding Insight SiP, Chris was responsible for setting up National Semiconductor's low temperature co-fired ceramic SiP design center. So with that, we will welcome Chris. And as Chris goes, we will make this an interactive presentation. So please submit your questions to the Q&A tool, and I will ask Chris as he goes. So the more interactivity here, the better. And I also see we have a few experts on the line too, which we could always call upon. But Chris, it's all yours.
Good morning, good afternoon, good evening. I'm Chris Barratt, CTO and co-founder of Insight SiP. And I'm going to talk today about design of very small multi-mode SiP modules, including 2 antennas. First of all, I'm just going to run through what we're going to talk about, a little bit of background on Insight SiP, and then I'm going to talk about what I mean by heterogeneous SiP. Then the next question is, what is antenna in package and why do we want to use antenna in package? And I'm going to illustrate the talk with some design concerning a module we recently produced for Bluetooth Low Energy, which is a well-known radio standard, and LoRa, which is a sub-gigahertz radio standard for long-range, low data rate, low power communications. I'm going to concentrate on two parts of the design process. Initially, the electronic part, and secondly, the antenna part, to give you an inside look into how this process can be done in an effective way. A little bit about the twin antenna design that we used in this antenna in package, system in package. A little bit about overall integration performance, and another twin antenna solution, which is quite interesting because it's being used in social distancing due to COVID. So Inside SiP was established by myself and Michel Bégan, I think he's online too, in 2005. And basically, we've always worked on RF SiP and going for ultra small solutions in the RF domain. And we concentrate on design and the manufacture through subcontractors, through OSATs, of RF SiP modules. Currently, our product line has Bluetooth Low Energy, LoRa, which we'll talk about, ultra wideband, which we'll talk a little bit about, and NB-IoT cellular types, which are the next generation of very small radio modules for IoT. I'm going to talk a little bit about the innovative antenna in package that we invented at Inside SiP in the early, between 2005 and 10, 2005, 2010. We're based in a fairly nice place on the south of, in the south of France, near Nice. This, the picture below is a picture of Antibes, which is really close by. As you can see, we have blue sea, we have an old town, and we have the Alps behind, where you can go skiing in the winter. So I'm now going to talk a little bit about what I mean by heterogeneous RF SiP. And it is really a complete 3D RF system that include many things. And typically it will include one or two system on chips. And the nice thing about it is you can choose different technology nodes. You can mix CMOS with gallium arsenide and silicon germanium and memory and put them in different places. We use any type of packaging technique that's available: flip chip, wire bond, package on package, package in package, BGA types. Everything that's available we can use in these heterogeneous SiPs. We obviously have to have passive integration, and often that's done just with very small SMDs. And we also use, in some products, integrated passives in glass, silicon, or ceramic. Substrate materials, typically today, we're mostly using organic BT type substrates, like most of the BGA and other SiP parts. We also have experience in LTCC and silicon integration for passive components. And the big thing about Inside SiP was, right at the beginning, we decided to try and input the antenna inside the package as well. And we have different flavors, either in the substrate, in or on the molding, or as a custom part in the molding. And all this put together can give you very, very small modules, which become more reliable than something put onto a printed circuit board. In the end, lowest overall cost and a much reduced time to market, because the radio is already designed when you start. This is just, I'm going to give you a little bit of background on where we were in 90, where we got to in 2000, and where we are now. In a radio system in the 90s, we had a printed circuit board with the transceiver, the baseband, the matching, and an external antenna. And then gradually, the idea came that it might be better to put a lot of the electronics in a single package. This is an example from 2002, I think. Actually, a module I designed at National Semiconductor. It's a Bluetooth module, as you can see, with two dies wire bonded on ceramic with quite a lot of passives inside a metal case. But the problem was we didn't put the antenna in, so the end user still had to create the matching network, the transmission line, and bolt an antenna on. And when we were starting Inside SiP in about 2005, we met quite a few people who thought it would be a nice idea to add the antenna. So after a little bit of work, we managed to miniaturize the antenna and put it in the package. So in the end, you end up with a single package which has absolutely everything you need for a radio node. This is an example, the picture is an example of one of our Bluetooth modules.
So Chris, is there a frequency limit to what can be done with an antenna and package? Because obviously, if your antenna is so big, it just doesn't fit in the package. I mean, so is there some frequency limitations?
You don't, yeah, we initially started in the 2.4 gigahertz ISM band and above. That's relatively easy because the wavelengths are such that it's relatively easy to miniaturize into a small package. We have then had to work quite hard to get a LoRa antenna, and that was a sub-gigahertz antenna working at 900 megahertz into a relatively small package. That's a bigger challenge, but it's a challenge which we've met, and we're currently also working on antennas for the low frequency NB-IoT LTE-M frequencies in the 700 to 800 megahertz band. And we're going to be successful there too. So yeah, it's a problem when you go down in frequency, but we've so far managed to get down to about 750 megahertz. So the principle of antenna in fact, thank you. The principle of antenna in package is in fact the final step to put the complete RF system into one package, and it makes this the RF component plug and play. And you don't need so much expertise to use it anymore because the antenna's there, the matching's there, the crystals are there, the microprocessor inside as well. So it looks a little bit like an RF microprocessor. And the other key feature about putting everything inside with the antenna is that particularly for FCC radio certification, it means that it's possible to have a radio that is completely certified and the end customer doesn't have to go through the complex, expensive process of recertifying the radio in his system. And that's only possible because we have the antenna bolted onto the electronics. This is just a quick roadmap of the history of how we developed AIP. We did some original R&D when we set up the company. And in 2008, we managed to produce a patent for the first antenna in package. And the first real module which we produced, a Bluetooth module, is still in production. And gradually we've moved forward. We had a second generation module in 2014. Murata came out with an AIP module in 2014. So it looks as though we're looking over our shoulder a little bit. It's always it's good to have a big company copying a smaller one. In 2016, we brought out the third generation version, still Bluetooth. And then from 2017 on, we started to diversify and add other radios to the Bluetooth. So we now have Bluetooth and ultra wideband for localization and distance measurement. And in 2019, we started development of an AIP with both LoRa and Bluetooth Low Energy in the same package. Again, just to remind you, LoRa is a sub-gigahertz, 900 megahertz, unlicensed ISM frequency for long range, low power, low data rate communication between a gateway and some sort of IoT device, a sensor or something that might be out in a field, or a cow or something that can be up to 20 kilometers from the gateway.
So, but you said a really low data rate. So, I mean, are we like Morse code sort of data rates, or? Yeah, I mean,
the nice thing about LoRa is it's got an adaptive, how should we say, an adaptive modulation scenario, which means that the further away you go, you maintain the connectivity at the expense of more time, so a little bit more power, and you can send up to a few tens of bytes per transmission. And then typically you might want to send a transmission every 15 minutes or every 30 minutes, depending on your application. It's typically for measuring a temperature or pressure or something at a distant object, water pressure, anything like that, where you don't need to send a lot of data, water meter reading can be done using LoRa. In Europe, quite a lot of water meter reading is now being done using the LoRa standard.
And they're able to do, you know, without, they're able to poll a lot of devices without, I know someone like,
yeah, because you don't have very much data coming out. Basically, you can get a whole load of devices on the same gateway without any big issues. Simply because the data rate's so small, the amount of data you're sending is so small. So any one device might be on air for 1 or 2 seconds every 30 minutes. So if you work it out, that's, you know, quite a lot of devices in the same area.
Understood. Thank you.
Okay, so the design example I'm talking about is the ISP4520, which you can see on our website. As you can see from the block diagram, it includes quite a lot of different things. It includes 2 radios. On the left is the MEPTEC LoRa radio with its TCXO or crystal and a DC-DC converter. Then we have the RF matching, the RX and TX matching. On the right, we have a microprocessor, which is also a Bluetooth radio from Nordic Semi, the NRF52832. There are 2 crystals that go in the package together with a DC-DC converter. And then we have a diplexer, in fact, in this design, so that we can use a multiband antenna to cover both frequencies, both the 2.4 gigahertz and 900 megahertz bands. And the module is a completely self-contained radio with both LoRa and BLE functions, with both antennas and all the frequency control and matching, plus a fairly good microprocessor. And as you can see, the finished product is quite small. It's roughly 10 by 17 by 1.7 millimeters and has an LGA interface.
So from a block diagram, obviously you've got a lot of things going on here and multiple domains, and maybe you're going to lead up to this, but what sort of tools do you have to, you know, tools do you use to design?
I'm going to come to that in a moment. We have a set of tool sets, which I'll explain in detail in a moment, which go from simple trace and route to 3D electromagnetic simulation. And it's a complex process, which is actually part of our DNA. We have always believed that it's better to simulate rather than just build parts and hope for the best. So this is answering your question. On the next slide, we show you the first part of the design process for the electronics. We start off with a schematic, as anybody might do, typically from reference designs for the different chips, which we put together, optimized for the component sizes. We're using Altium as our trace and our schematic to layout tool. You can also use Allegro SiP, Expedition from Mentor Graphics, and other tools. We just chose Altium because it's a fairly good cost-effective solution for our needs in a small company. So first step, you have to capture the schematic. And then all the components will have their individual footprints, and you transfer the footprints to the substrate domain or the layout domain. And you start off by placing the components. And compared to a PCB, we place the components much closer together, but basically it's like a PCB. And as you can see, we have some flip chip components, some crystals and some passives in there. And we route the substrate basically using what I call best design practice based on experience and RF knowledge and decoupling knowledge, being careful to shield paths that are delicate. And even this process, which is basically using the Altium tool, is fairly iterative until we get to a solution which we like. And it is actually a key task requiring experience before you go to the next step. And the next step is also extremely important to avoid looping too much in the manufacturing phase. So what we then do is we extract the 3D layout of the substrate, which we designed in the previous step, simulate it with a 3D tool, typically ANSYS HFSS, could also use CST or ADS FEM. From the 3D EM tool, we create an endport S parameter model, which we then export to our schematic simulator, which in our case is Keysight ADS. And at this level, we add components and optimize and try to get the optimum performance just by tweaking component values. If that doesn't work, we go back to the start, change the substrate a little bit, and redo the whole process. At the end of the day, this process, if it's done correctly, will reduce the number of design spins where you actually manufacture something, improve overall performance, and improve time to market, because the design process when you stay within the tool is a lot quicker than the design process when you actually build a substrate, have it assembled, and have it tested. And this is some pictures of the design process. On the top right, you can see the layout that has been extracted from the layout tool into a 3D simulation tool. All the little green squares are actually the ports where there are components. And basically from the EM simulation, it boils down to a block on the left in the middle, which is a block of S parameters that is describing the functionality and the coupling and the interaction of all the ports on the right-hand side. And at this level, we can add components and we can run the optimizer to optimize component values. And we can simulate all the RF paths that there might be in such a device, look for cross-coupling, look for any things that might not be working correctly, get the matching right, and basically get the complete design more or less 100% right first time before we start building anything. Again, this process can be iterative. We can, in some cases, have to go back to the Altium tool to modify things. And when we've done a first spin, we often use it to determine how to adjust the values of the components to get optimum performance. So that gives you an overview of the design process for the electronics part. And now I'm going to move on to the process for the integrated antenna design. Now, when you do an integrated antenna design, there are a number of design constraints. And the first one we talked about earlier is how do you get the thing into the package? And we've learned that you have to be careful and you have to try and push to reduce the size of the antenna so that it's roughly 2 to 3 times smaller than the discrete antenna. And of course, you try to keep the performance as close as possible to the discrete antenna, but it's going to have an effect on the range of your radio. Then we've decided in the antenna in package, you have to use the standard SiP technology, which you're going to use for the electronics. Sounds obvious, but it means that it forces you to design antennas that will fit into that technology, be it LTCC or organic substrates. And we have a number of options for the place where we put the antenna. We favor things that use the parts of the technology that are already there. For example, we like to put structures in the substrate. We like to put structures in or on the mold compound. Sometimes we put them into passive devices, which we build specifically, and sometimes we use SMT components. When you do the antenna design, you have to look very carefully at performance margins because the module is actually going to be in an environment where it's sitting on an application board. And we know that the application board is going to have an effect on the antenna performance. So we look fairly carefully at this during the design process of the antenna to check that the antenna will have acceptable performance over a wide range of ground plane sizes and positions on the application board. And we also take into account production tolerances, dimensions, material properties, dielectric constant, dielectric loss, and stuff like that. And we're looking for best return loss over the operating band, a good radiation efficiency in the operating band, and patterns for radiation and gain.
So Chris, with this, you obviously doing the simulation to try to get the design right, but is there anything that you end up doing prototype-wise? Do you end up prototyping the antenna structure and making some measurements, or is it you wait till you have the whole SiP together?
Typically, we like to separate the problem into 2 parts. We know that the tools for doing antenna design are the same as the ones used for the fine-tuning of the substrate design for the electronics part. But nevertheless, the accuracy is such that we do need to do some prototyping. So typically we try to build an antenna with the same topology as the final antenna, maybe not exactly the same topology, technology, maybe not the same fine substrate, but something we can do locally, quickly, and do measurements in the lab, and then feed that back into the simulator. So we're sure that the performance of the antenna is actually going to be close to what we want. And in the final design process, in the first run of a module, we tend to do a pizza mask. So we may lay out 3 different variants of the same antenna so that we don't get the antenna at the wrong frequency. So we can pick the one that works best at the right frequency, exactly the right frequency. Typically they all work, but sometimes they're a little bit off frequency. And we don't have any tuning very often in the components. So it has to be out of the box correct once we've got the design finished.
Okay, and so good. So I have some questions here, some other questions. How do you minimize the insertion loss of the RF signals in the different materials or to the ground plane?
Okay, well, basically we're typically today using BT substrates. And the BT substrate has a relatively good dielectric loss tangent. The other thing we're doing is we're making things very small. So the amount of distance that the signals have to travel is extremely short. So that helps us with the loss parameters. The other parameter, which is a bit of an issue, is the fact that we want to use the smallest passive components that we can. And particularly the inductors, there's a trade-off between component size and the quality factor of the inductor, which impacts the insertion loss of the matching network. So we evaluate that during the schematic phase of the design process using component models from the component suppliers and making trade-offs between cheap, more expensive components, smaller components, and bigger components.
Okay. Makes sense. Okay. And a different question is, you talked about different ways of building the antenna. One person was asking, do you have experience with overmolded chip antennas in the package? And the follow-up question is, what's the impact of the mold on the beam forming and the transmit receive performance?
Okay, the first question is, we have not put any commercial antennas in the overmold compound because we don't have an electromagnetic model or design of a commercial product. So we've excluded putting ceramic chip antennas inside our overmold because we haven't got a design for a ceramic chip antenna. We don't know what's going on inside. However, we have designs where we use our own design of an antenna, which we place within the overmold compound. And our experience is, and we design with the overmold compound. So if we design an antenna which has, for example, something in the substrate, something in a second piece of organic material above the substrate and the mold compound, we take into account the dielectric constant of the mold compound, the dielectric constant of the component, the metals, the position of the metals, and so on. So typically we take that into account. With regard to radiation pattern, because the antennas are so small, the radiation pattern is not significantly affected by the overmold. It's going to be more affected by metal that you place in the application around the module than it is by the overmold compound itself. And in any case, the overmold compound is actually a part of our design. When we do the complete design of the antenna includes substrate, the application board, the whatever we put inside there, plus the overmold compound. Okay, so I'll go back to what I was going to talk about, which is the design process, based a lot on background knowledge and design experience of antennas. Nevertheless, we make extensive use of ANSYS HFSS. We look at different topologies with different mechanical structures, with different dimensions. We try and tweak the dimensions to get optimum performance and do a whole range of batch EM simulations to get to something that looks nice. We then make a schematic model often of the antenna, tune the parameters, and then go back to a full 3D model of the device. and choose the best one, obviously. And we may, for a given module, look at several different options. Certainly the case in the example, we did look at lots of different options. In the case of the LoRa BLE, as I said earlier, the big challenge was to get the LoRa sub-gigahertz frequency antenna into a small size. The miniaturization is quite complex because of the dimensions of the wavelength, which we can't do anything about, unfortunately. That's related to the dimension, the wavelength in air of the frequency. BLE is a bit easier. The quarter wavelength, which is critical for the antenna, is roughly 3 centimeters. And during the design process, we actually looked at 2 different options. One option was to have 2 antennas, and the other was to have 1 antenna with 2 different modes and a diplexer. And we experimented both options, in fact, and we found that the second option with 1 antenna and 2 modes was actually more effective, because we didn't have to worry so much about coupling between the 2 different antennas, which was causing problems of loss of signal from one antenna to the other. We then looked at different integration options in this particular case. The first option, which is the simplest option, is just to print the antenna as a meander in the substrate. But in this case, for LoRa, it doesn't give satisfactory performance in the dimensions we wanted, because there isn't enough volume, basically, antenna. So we then went to 3D structures using vertical vias in the mold compound, with metal on the top of the mold compound and metal in the substrate connected by vertical vias. And as an alternative, a 3D structure in a purpose-built component in an organic material, which is placed as a component in the mold compound. Again, we built prototypes of both versions, and in the end, we've opted for the third option, the component in the mold compound, because it turned out that it was a cheaper option and easier to have different SKUs, because you just change the antenna component. Even if it's designed as an integrated component, you can have 2, one for the European band and one for the American band. This is a little picture of the module. I'm really showing the antenna as a lump of organic material with stuff printed on top. You can't see what's printed on the bottom, so you can't really see how we did the antenna, but it gives you an idea. It's a corkscrew type antenna, if you like to look at it. The electronics on the left is not actually simulated completely when we do the antenna design, but we put at least the substrate and metal in the substrate and the metal shield, which in fact is printed or sputtered onto the overmold material to protect the electronics. Again, we do a lot of EM simulation at this level using ANSYS, and we try and optimize the design so it work on different main application PCBs. You can see here we've excluded metal on the main application PCB under the module. That's what we recommend, or it's necessary. And then we also want, in this particular case, the module to be placed on the edge of the application board. And then we looked at different application board sizes. This is one of the results of the simulation. It shows quite good radiation pattern for the LoRa antenna. We lose a couple of dBs compared to a bigger antenna, but it's still quite acceptable for most LoRa type applications. And then a little bit about the fabrication of the device. We're using standard OSAT SiP based manufacturing. We're using quite a large panel that you can see on the top right. Basically, the process is to start off by mounting all the components. In this module, we don't have any wire bond components, so it's basically an SMT process. As you can see, we have a flip chip component. That's the Nordic radio and microprocessor. We have a QFN component, which is actually a package inside the package, inside the overmold, because we couldn't source the die that was available because it's not tested. We had a small switch and 2 crystals, a TCXO, and a whole load of passive components. After the components are mounted and the antenna has been mounted, we go for compression molding to create over the whole panel a flat area. We then metallize over the electronic part to shield the electronic part using a sputtering process, separation, and final test. And
so
that's
a question was, why do you use compression molding versus transfer molding?
We use both. There is a move in the OSAT market away from transfer molding, injection molding, because you get slightly better overall performance, slightly less voids in the process. And we found that it gives overall a better performance from a technological point of view. With transfer molding, we often, in our designs, we have to use underfill under some of the components to ensure we don't get any bleed during reflow of the SiP at second level interconnect when we put it onto an application board. In the case of compression molding, the compression molding material goes better underneath the components to create a seal around the solder joints. I'm now showing you I'm now showing you another module which we developed initially for real-time indoor localization or measurement of somebody relative to a fixed object. And we've recently done some adjustment of the firmware so that we can use it in a COVID-19 social distancing product. And we're at the development stage, but we have already a prototype using our module that actually indicates when people are too close together and gives an alarm. And as we're using ultra wide band in this product, the actual accuracy of the measurement is something like 10 centimeters. So compared with some solutions using Bluetooth Low Energy, it is an order of magnitude more accurate. Bluetooth Low Energy, you can be anywhere between 1 and 4 meters when you think you're at 1 meter. In this case, because we're measuring using a radar technique, time of flight, we get the accuracy to about 10 centimeters. And the idea is that people wearing the object, when they get too close to each other, they interact and they have a buzzer or a vibrator that tells them they're too close and they move apart again. And if you want, you can go to the YouTube and look at a little video we've produced. You can either copy the link at the top of the page, or if you type YouTube Insight SiP security bubble on Google, you get to the same video and you can see how this is meant to work. Well, thank you for listening patiently. Thank you for your questions. If you have any more questions, I'll be more than willing to answer them.
Okay, so yeah, well, we do have a few more queued up. So one of the questions was, how do you solve EMI issues such as antenna descents with the high level of integration with the tightly packed components and integrated antenna? Does that really restrict your solutions space, or how do you work towards those challenges?
Basically, because we are doing two things. First of all, the electronics is shielded by the metal that we plate on top of the overmold compound, which is connected to the ground plane inside the module. So if you like, the electronics is to some extent protected from the radiation coming out of the antenna. And then the other thing we do, of course, is we co-simulate the antenna with the electronics so that we can see what the interactions are likely to be. We don't tend to have absolutely everything in that simulation, but we do tend to see most of the problems. The other thing we've noticed is that if you do electromagnetic simulation of the substrate, you isolate the coupling effects that you might otherwise ignore before you actually get to building anything. So typically we know how to create very high isolation between adjacent paths by careful routing, careful protection, and sometimes using what I would call interactive neutralization, where you get two signals in opposition, in phase opposition, to cancel each other out.
Understood. And then another sort of a design related, can you accommodate antenna arrays in the small SiPs?
Okay, we have, in the past, we were a company doing design service and our own products. Today, we're more a product design company. And we did designs of antennas arrays for high frequency. Typically, the problem with an antenna array at low frequency is you need to space the antennas by something like a half a wavelength in air. So it's prohibitive in a small package at Bluetooth frequencies. If you go up to the 60 gigahertz band, it's a pretty good environment to do an antenna array, either a 2D or 3D or 2D or 1D antenna array. And we have done some designs of antenna arrays with patches on the top of the substrate, essentially. But for most of what we're doing today, any sort of antenna array would be outside the scope of the SiP itself.
Okay. Especially in the, as you said, in the frequencies you're working, right? So
yeah, it's due to the frequencies, yeah, and the physics.
Yep. We had a question on test. Is there, any particular structures like DFX structures that you put into the SiPs to allow cost-effective production tests? Like the 900 megahertz and 2.4 gigahertz RF transceivers. I mean, is there certain hooks you put in to enable production tests?
Yeah, one key thing that we have designed into absolutely every module we built is the fact that during certification and production test, you want to be able to input and output radio signals directly to the electronics. So typically what we have on the package is for each radio, we have the RF out and an adjacent pin, which is antenna connection. So when you want to do the production testing, we're in a conducted mode where you just look at the sensitivity and transmit power of the RF electronics. And when the customer wants to use the module, he just connects on his application board the two pins together directly. And we rely on visual inspection and substrate shorts and opens testing for an accurate check on whether the antenna is correctly built or not. And we've built many millions of parts and never had an issue with the antenna not being connected in the actual device. The other thing we do in our testing is we concentrating on testing functionality. We don't try to retest the chip as though we're trying to test absolutely everything in the chip. We try to make sure that the chips have been connected up correctly. So we check connectivity, but we don't retest all the functionality of every chip. We check that all the pins are connected, and we assume that the testing at the chip manufacturer or the packaged or flip chip device is 100% good. So we're not retesting that. We're just checking we're connected up. We check the radio's working and all the IOs are connected.
And so related to that, what's your experience with acquiring bare die or die in wafer form?
We have quite a lot of experience. Yeah, with our own products, we have typically used WLCSP parts or QFN radios. There were two issues with buying wafers. We bought wafers in many different solutions we've built over the past 15 years. The difficulty with wafers is some of them aren't 100% tested. So that means that the known good die issue is a problem. Often there's a very high initial order required or a project requirement for very large numbers, which we don't always meet on our product lines. So we've learned to be pragmatic. The easiest thing to procure in wafer is memory. We built a complete Linux computer in a micro SD using very thin memory from Micron in the past. But to do RF SiP, very often the problem is the device is either tested at RF or it's not. If it's not tested at RF, you're going to have to pay an awful lot and buy an awful lot of parts before you can buy wafers. So the start of, for a small company as well, the start of a project where you might have to buy 500K of inventory to start the project is just a non-starter. So we've learned to be pragmatic. In the BLE LoRa solution you saw, we're using a QFN, a very small but still QFN packaged part for the LoRa radio, simply because the LoRa radio doesn't exist in a tested die format, neither in a wire bondable format nor in a flip chip format. Our preference is to use flip chips, frankly, because it's the best solution for a SiP. But we have to be pragmatic because we're doing heterogeneous SiP, and you can't impact the way they do the wafers. You're second tier relative to the wafer manufacturer.
And this question probably relates to that, but it veers into the commercial domain. But there's one of the attendees wanted to know what products do you have in volume production, and yeah, I think you've sort of touched on some of it, but.
Yeah, I mean, we started off in Bluetooth Low Energy, and we have a whole range of products in volume production for Bluetooth Low Energy. We have engineering quantities of the ISP4520 UWB Bluetooth, the ranging device, and we're in the ramp-up phase for the LoRa BLE. So if you want to buy LoRa BLE, we can support you today with development kits and parts. For UWB, the same thing, and we're in high volume manufacturing with multiple OSATs for all the Bluetooth Low Energy range of parts. We basically have a Bluetooth module for virtually every Nordic Semi chip, of which there are about 10 today. So we have quite a big range. If you go onto our website, you'll see the parts. Basically, the Bluetooth is the thing that's enabled us to grow. And we think LoRa will be the next thing, and ultra-wideband after that.
Good. One last question to wrap up, and I think the question reads, have you used chip antenna in your design? So I'm assuming that's a piece of silicon designed as an antenna, or?
A chip antenna could be ceramic, it could be silicon, it could be a piece of PCB. As I said earlier on, we only use antennas that we've designed, for the simple reason that it's not easy to get a good 3D model that we can put into HFSS for chip antennas that you buy commercially, because we need to do that to be able to work out how it's going to work in the environment of the SiP. Because typically a chip antenna, the manufacturer will give you an environment which is often quite big around it, and if you don't use that environment, then it's a lot of cut and try to make it work in a smaller environment. We don't like to go that way. We prefer to simulate, and we can't simulate with a third-party commercial chip antenna. And we get, actually, to be frank, we get better performance with our own designed antenna in Bluetooth, typically in the substrate, and in LoRa BLE in a component above it. So yeah, so that's the way we've gone. It's not the only way to go, but it's the way we've gone.
Great. Well, thank you, Chris. If there are other questions, I'm sure you can reach out to Chris. And I'd also like to thank you again for presenting, and also mention that in this month, or in the current issue of the MEPTEC report, the president, Nick Wood of Inside SiP, has an article, SiP-based RF modules squeeze more functionality into devices. So that's on the MEPTEC report, the spring 2020 edition. You can get it on our website. I'd like to thank Chris. In conclusion, reminding everybody that the next MEPTEC IMAPS Semiconductor Industry Speaker Series will be on July 1st. Stephen Rothrock from AT-Reg, July 15th. Jan Vardaman from TechSearch International. And then on June 30th at 9:30 a.m., we'll have the panel discussion for the Known Good Die workshop about the need for known good die. And with that, I'd like to thank everybody and wish you all a good rest of your day. Thank you.
Thank you.